Chapter 7 is the whole chapter about symmetric matrices and some of the results that come out of symmetric matrices. And so we'll start with 7.1, where they talk about symmetric matrices and diagonalizing symmetric matrices. So what's a symmetric matrix? Symmetric matrix is a matrix so that its transpose is equal to itself. That seems pretty obvious. The symmetry goes around about the diagonal. So if you look at the diagonal, everything opposite of the diagonal should be equal. And the diagonal could be whatever it is because it's in the diagonal. That's where the symmetry happens. But everything else around the diagonal should match up. And that's the idea behind the symmetry. So let's take a look at this matrix and diagonalize it. What does diagonalize mean? You remember how to diagonalize something? Let's eigenvectors. Let's find eigenvectors to diagonalize, and then you know how to diagonalize, right? Eigenvalues, eigenvectors, and use all that stuff. So can I just use the computer? That's well, see, no, that's the thing, is that you'll need to be able to do this on your exam. And so I was thinking that since you already know how to do this, I don't have to waste time in class finding the eigenvalues and doing the whole process because you already know how to do it. Okay? So let's go to Wolfram alpha. We got like all kinds of choices for our processes here, right? We can do Wolfram, we can do MATLAB. Probably, I don't know off the top of my head. So there's a command in Wolfram in mathematics called eigenspace, and you put in the matrix, and when you put in the matrix, you got to go row by row. So 3 minus 2, 4, and then each row is like a list, and a list in Mathematica is obtained by writing curly braces. So when we do the eigenspace, they call it, maybe it's eigenvalue. It provides what we would call an eigenspace, and then it would have the list of eigenvalues and eigenvectors. So let's take a look at this result, and this is an interesting set of results because we have an eigenvalue of multiplicity 2, and the eigenvectors that are involved in there are these vectors here. Why can't I put it next to each other? I don't know. So according to the diagonalization, if this is the eigenvalues and the corresponding eigenvectors, this should equal to, what is it, P inverse or P first? I forget. P first, and then D, and then P inverse. And then we would write down what P is equal to, and then we would write down what D is equal to. So I think I know what D is. D is just the eigenvalues in a diagonal. D, remember, is a diagonal matrix. And then P is what? So the corresponding vectors, so V1 and V2 correspond to the eigenvalue of 7. So let's say 1, 0, 1 for that first column, negative 1, 2, 0 for the second column, and then minus 2, minus 1, 2. Okay, so that's diagonalized. No, that doesn't seem so interesting. It seems like stuff that we've done already. So I wonder what's new. Yeah, but that's what we got last time. We should have gotten that anyways, right? Well, this is probably not so obvious, but what might be different about this is that if we look at the different eigenspaces, we have two eigenspaces here. One eigenspace corresponds to the eigenvalue of 7. So the eigenvalue of 7 has a two-dimensional eigenspace. It's spanned by these two vectors. And then we have another eigenspace that's a one-dimensional eigenspace. Okay? Does that make sense? All right. So the different eigenspaces, it turns out, are, again, this is not so obvious until we start looking at the theorems in the section, but consider the eigenspaces for lambda is equal to 7 and lambda is equal to negative 2. If you take a look at the eigenvalue or the eigenvector for that lambda is equal to negative 2 space, and compare that with the eigenspace that you got for V2, or for lambda is equal to 7, that's V1 and V2. It turns out that they're actually orthogonal. And that's the interesting thing about this is that this is not a coincidence that this happens for symmetric matrices. So what does that mean that they're orthogonal? So V1 dotted with V3. So if you take 1, 0, 1, dot it with V3, minus 2, negative 1, 2, what do you get? 0. V2 dotted with V3. So V2 is minus 1, 2, 0, and then you're dotting that with negative 2, negative 1, and 2. What do you get? You get 0 again. So you could dot V1 and V2, and you may or may not get 0, but since they're in the same space, we're not going to consider them we're not going to mandate them to be orthogonal. But the different eigenspaces that come from different eigenvalues turn out to be orthogonal. So that brings us to an interesting theorem for symmetric spaces or symmetric matrices. So if A is a symmetric matrix, then any two eigenvectors from different eigenspaces are orthogonal. And here's a proof. That looks a lot nicer in the book instead of just one line like this. But let's see if we can break this down. So the theorem says that if you have a symmetric matrix, then any two eigenvectors from different eigenspaces are going to be orthogonal. So that's the example that we just saw. So how did they prove it? They proved it by taking a look at this this dot product process. They want to show that v1 dot v2, assuming that they're coming from different eigenspaces, it's going to be 0. So this actually the string of inequalities don't show everything, but let's take a look at see how far it goes. So let's see, maybe we can justify each step here. A lot of steps if you break it down. So let's take a look at this first step. Lambda times v1 dot v2 is equal to, so this is a dot product here. And now this becomes kind of like the definition of a dot product. It's matrix multiplication. So the dot product, remember, is really just a matrix multiplication of the transpose of that vector dotted with multiplied by the other vector itself. And then now in this step over here, well, how can you justify this next step? So an eigenvalue times its eigenvector should equal to the matrix times the eigenvector, right? So that's a definition of an E value and E vector. And now the transpose of A, the matrix A, multiplied with the vector V, which is, again, the matrix, the transpose of that is equal to the transpose of each individual one multiplied in different orders, right? So this is a matrix transpose multiplication, something like that. Yeah, it's a property that we saw. And then now with associativity, you can attach, well, before we attach, A is symmetric. So the transpose of it should equal to A itself, right? And then we can use this definition of the eigenvalue again to change your matrix to lambda. And then we can play around with a couple of other. This is a associativity of a scalar in matrix multiplication. So it's one of the properties for matrix multiplication, and that if you have a scalar, you can move that outside, and then this is changing this into a dot product again. So what do we have? We have, so I guess this isn't finished yet, so let's finish it off. What we have here is that lambda 1 times v1 dotted with v2 is equal to lambda 2 times v1 dotted with v2. So the assumption is that lambda 1 and lambda 2 are not equal to each other. So that must mean that v1 and v2 have to equal to 0. Okay. because you're not guaranteed that lambda 1 is going to be equal to v1 and v2 and lambda 2. Well, that doesn't make sense. So this implies that v1 and v2, or v1 dotted with v2, has to equal to 0. So that proves that they're perpendicular from each other. So we saw that in our example. Now this is the general proof for doing this. Okay? So that's interesting. We have a symmetric matrix. We find eigenvalues. The eigenspaces are going to be perpendicular from each other. Orthogonal. I guess we should use orthogonal. All right, let's see. So there's another definition, basically what we kind of did. So the diagonalization that we did was the getting that diagonal and then having the PDP inverse. So a special type of diagonalization is if you have an n by n matrix, it's said to be orthogonally diagonalizable if an orthogonal matrix P and a diagonal matrix D can be paired together so that PDP inverse is the same thing as PDP transpose, since the matrix P is supposed to be orthogonal. And does it need to be symmetric? Well, in the next theorem, it turns out that you could do this if you have a symmetric matrix. And if you don't have a symmetric matrix, then it's either not doable or really hard. Well, let's take a look at the next theorem. So remember that an orthogonal matrix means that the columns of your matrix are not only orthogonal, but they have to be of unit length also. So yeah, I know. They should. Let's put orthonormal. Because when we defined orthogonal matrices the first time, they made a big deal about that, saying this is, people usually say orthogonal matrices, but they actually mean orthonormal. So let's take a look at the next theorem. Probably need to change that title later. If you have an n by n matrix and it's orthogonally diagonalizable if and only if A is symmetric. So it kind of hinges on the idea that A transpose is equal to A, but if it's orthogonally diagonalizable, then that means you can find a PDPT, or P inverse really, but then it really becomes a PDP. I guess maybe we should squeeze that in here. So to say that something is orthogonally diagonalizable, that means that PDP inverse is the same thing as PDP transpose. And so if you want to take A and take the transpose of that, then you would have PDP transpose is equal to, or to the, and the transpose of that. And the transpose, remember, you switch the order of the multiplication and take the transpose of each one. So transpose of P transpose of D, and then the transpose of the first P. And then you get this thing, which is equal to A anyways. So that says that A transpose is equal to A, so that shows that it's symmetric. and if that symmetry works if it's diagonalizable. So I think the set of inequality or the set of equalities show that it's the proof goes both ways. So let's try to orthogonally diagonalize. Orthogonally diagonalizable. That example that we just did. So in this example, is this the orthogonal diagonalization? Orthogonally diagonalizable. So we have an issue, right? So let's see. So this is equal to, what's this equal to? P inverse, where P, what was P equal to again? 1, 0, 1. What? Negative 1, 2, 0. 2. And then D was 7, 7, negative 2. So what we want to do is we want to see if we can orthogonalize this. This isn't quite orthogonalized yet. So let's see if we can orthogonalize these two vectors or make them orthogonal. Are they orthogonal already? 1, negative 1, 0, and 0. Nope, it's not orthogonal. So how do you, we'll keep this as our first vector. What? Well, they're not orthogonal yet either because the middle one is not quite perpendicular to the first one. So how do you make the second vector in here orthogonal to the first vector? The Gram-Schmidt process. Remember that? So it's there's only two vectors we're checking, so it's really not really, we don't even have to think about the Gram-Schmidt process. It's like that stuff that we learned in Calc 3 or at the very beginning of orthogonalization, where we're just projecting it onto one other vector. That's all we're doing, right? So we're projecting it onto one other vector, and that's going to be, if we call this vector, I don't know, V2 is equal to, or V2 minus, and then the projection of V1 onto V2, which is V1 dotted with V2 over V1 dotted with V1 times V1. So let's take the dot product. So V2 is equal to minus 1, 2, 0. And then we take the dot product of V1 with V2. We got negative 1 on the numerator, and then denominator V1 with itself. Is that negative? That's square root of 2? No, it's just 2. So we have minus 1 minus negative half, positive 1/2. 2, oh, that's just 2, and then 0 minus negative 1/2. So this should be perpendicular to V1, right? Negative what? Negative 1/2? Yeah. Yep, thanks. So negative 1/2 to positive 1/2. And then, so this is still, I mean, we hope that this is still going to be perpendicular to V3, right? Because V3 is perpendicular to the space that spans V1 and V2. So regardless of which vectors span V1 and V2, it should still be in that space. Wait, hold on. There's a question back there. Positive? Oh, yeah. Thank you. All right. Because we want to create an orthogonal matrix for P. They don't what? Well, but aren't we trying to find the orthogonally diagonalizable, the orthogonal diagonalization? Yeah. Because we want to create an orthogonal diagonalization so that we have, instead of just regular P, we have P inverse, which is going to be equal to P transpose. Yes. Oh, yeah. No, it shouldn't, because V1 and V2 are in a separate space on its own. They're the eigenspace for lambda 1, or they're the eigenspace for lambda is equal to 7. Remember, 7, since 7 has multiplicity 2, its eigenspace is two-dimensional. And so whatever happens in that space is a plane. Whatever happens in that space isn't going to matter with a third eigenvector eigenspace, because it's going to be perpendicular to that plane anyways. So what we have is V1 and V2 span the plane, but they don't necessarily have to be perpendicular, and V3 is perpendicular to both of them. And what we did was we changed V1 and V2 so that they're now perpendicular, but that still doesn't change the V3. The V3 is still going to be perpendicular to all of them. I don't think so. It shouldn't, because when we find our eigenvectors, we can scale them we can scale them as we need to. It's just that when we find the inverse of them, we have to make sure we use the correct inverse. All right, so just to double check though, let's take the dot product of this newly found V2 with V3 to make sure that they're perpendicular. So negative 1/2 times negative 2, that's positive 1. Negative 1 times 2 is negative 2, and positive 2 times 1/2. I lost it already. Where am I? Is that 0? That's 0. Okay. So the idea is to check to make sure that they're still going to be perpendicular, to check that V2 is going to be perpendicular to V3. So anyways, let's create our unit vectors by just finding its magnitude, dividing. So this V1 has magnitude 2, square root of 2, square root of 2. So our U is going to be 1 over root 2, 0, 1 over root 2. Now we need the magnitude of this. Maybe we can scale this. What happens if we multiply everything by 2? So this is negative 1, 4, and negative 1, 4, and positive 1, right? So what's the magnitude of that? 16, 17, 18, square root of 18. So negative 1 root 18, 4 over square root of 18, and positive 1 over square root of 18. And then the last one is 2, 2, 1, so that's 4, 8, 9, square root of 3, or 3, square root of 9. All right. So this is our the P that we would like to use. And so if we set up our P to be 1 over root 2, 0, 1 over root 2, negative 1 over root 18, 4 over root 18, 1 over root 18, and negative 2/3, negative 1/3, and 2/3. The what? Wait, what's the null space? Eigenvectors? Oh, yeah. It should be, because it's either just stretched out or is a linear combination of two vectors. So the null space of 7, lambda is equal to 7, is a two-dimensional space, which means anything in that two-dimensional space is going to go to 0 with the null space of that thing. So not only do we have P, but P inverse is going to be easy to compute because P inverse is just P transpose. So P inverse equals P transpose, which is equal to just the transpose of this, 1 over root 2, 0, 1 over root 2, 1 over root 18, 4 over root 18, and 1 over root 18. And thirds. And you still have the same D. So hopefully if we multiply this out, we're going to get the original matrix. If it's an orthonormal if it's an orthonormal matrix, then it should be. And it should have the transpose is equal to the inverse. Yeah. Jesse? All right. Should we multiply it? Kind of afraid to. What if it's wrong? Oh, I know what. We'll use Mathematica. Sometimes I forget. All right, so we'll let P equal to 1 over, square root. Yeah, here we go. Square root of 2. And then the next row is negative 1 over square root of 18. Eventually, yeah. 4 over this. 1 over that. And minus 2/3 minus 1/3 2/3. So just look right. That looks okay. Suppose I can make it bigger. We don't have Josh in my other class squinting back there saying, "What? Can't see." So the inverse of P should be, it's not singular. I wanted P. I guess this is what I wanted. I think I put P transpose, huh? Oh, I put a negative here? I took the transpose. Oh, crap. All right, let's try it again. So let's move things around. This is a second, and then this is negative just 2/3. This should be a 0. 4/18, and this is a negative 1/3. And then this is let me put the 1/18 here. Yeah, so I'm entering them as rows, so now I have rows. So does this look like this matrix here? All right, so let's find the inverse. I guess we should make this matrix form so we can see it. Oh, I think I missed a negative sign somewhere here, right? So I think if this is just all equal to simplifying it, I'd say it's the same. Does that look okay now? That's a transpose of what's up here. Oh no. So now let's multiply P, multiply that with the diagonal 7, 0, 0, 0, 7, 0, and 0, 0. What was it? -2? The last one. Oh, there it goes. Is that the same? Yes. Phew. Okay. So it looks like it worked. So let's just, it's worth putting all this Mathematica stuff in the notes. Sure. Oops. There we go. We have some stuff in the notes. All right. So any questions so far? Diagonalizing and making sure that you're create an orthonormal matrix, and then doing that multiplication. All right, let's see what's next. Spectral theorem. All right, so let's take a look at this spectral theorem. Spectral theorem for symmetric matrices. If you have an n by n matrix that's symmetric, then you have the following properties. You have n real eigenvalues counting multiplicities, so you have a complete set. This thing is going to be a complete set of eigenvalues. The dimension of eigenvalue, or the eigenspace for each eigenvalue, equals the multiplicity of y, or the multiplicity of lambda from the roots of the characteristic equation. So I don't know if I think I might have mentioned the difference between an algebraic multiplicity and a geometric multiplicity. An algebraic multiplicity is the multiplicity from the characteristic equation, and the geometric multiplicity is the dimension of the eigenspace. So we didn't actually do, like in this example that we were doing, we had Mathematica or Wolfram Alpha figure out our eigenvalues, but had we went through the process of finding the characteristic equation, the characteristic polynomial, well, we would have seen that 7, lambda is equal to 7, would have multiplicity 2. And then in this process, we saw that the geometric multiplicity, or the eigenspace that it spans, is two-dimensional. So that's what the eigenspace multiplicity and the characteristic equation multiplicity is, that they're saying that they have to match. There are some cases where you have algebraic multiplicity to be 2, but then when you try to find the null space, then there's only one-dimensional, so you kind of lose a vector that way. But that's not going to happen if you have a symmetric matrix. The third thing they say is the eigenspaces are mutually orthogonal. So the eigenvectors corresponding to different eigenvalues will be perpendicular. If they're corresponding to the same eigenvalue, that they might not be perpendicular, or they might not be orthogonal. Like in the example that we did, we had 7, eigenspace is dimension 2, and those two vectors did not start off being orthogonal to each other, but we made it orthogonal by using some sort of projection and stuff like that. And then the last thing is it says that A is orthogonally diagonalizable, which means we can certainly find this special matrix P, an orthonormal matrix, so that its inverse is a transpose. Okay? So that's the spectral theorem, but I think more importantly is the actual decomposition. So there's this thing called the spectral decomposition, and the idea behind this spectral decomposition is that we want to be able to take a matrix that's orthogonally diagonalizable and then break it down to different components. And we might be able to call those components as spectrums, where the matrix A is actually equal to the product, or not the product, but the sum of a bunch of matrices, and that's scaled by the eigenvalues, which is pretty amazing. So what do we have here? We talked about the spectral theorem already. Spectral decomposition says that you were able to decompose your matrix into the orthogonally diagonalizable decomposition, where P is an orthonormal, a set of orthonormal eigenvectors, and then A corresponds to lambda 1 through lambda n, diagonal matrix. Then this is going to be what it's going to equal to. And what they're doing here is they're essentially taking the columns and they're not taking the inner product, but so when you see this, you should be alerted that, hey, that looks like it's just the inner product, right? The dot product. But this is not actually the dot product. The dot product is U1 transpose times U. So when you switch the order of U1 transpose and U, like in this case, what do you think is going to happen? What are you going to get? It's the outer product. Remember I mentioned the outer product? You're actually, when you dot two vectors, you're going to get a scalar, right? Or think about it as a 1-by-1 matrix. But when you dot it the other way, you're actually going to get an n-by-n matrix. So what you have here are a bunch of matrices. You've decomposed this into the matrices that's based on those orthonormal column vectors. Yeah. Yeah, this is for symmetric matrices. Correct. Yeah. So let's take a look at the decomposition for that example that we've been running on. So we have our example already. Let me see if I could just copy. Yeah, it's too much to copy. I just copied this problem. Is there room here? So we have we found a new P, right? The new P that we got is actually ortho something. So it was minus. Was it minus a half, or is it positive or negative? It's positive. Yeah, 0. And then this next one is and 4. And then the last one was. Thank you. Our D was 7, 7, negative 2. And our P inverse is P transpose. So we should actually say P, D, P transpose. But it's the same thing. So what we want to do is we want to take a look at each of these columns for P as the outer product. So I guess I have to type that in. I just copy it from somewhere. So U1 is going to be equal to this. U2 is going to be equal to this. And U3 is equal to this. So let's see, U1 simplified in matrix form. Oops, I didn't press enter. All right, and then, so U1 dotted with U1 is going to be a number, whatever that number is. But if we take the transpose of the second one, oh, I need to make this into a matrix. I don't know. I don't know what's happening now. I think this is what I was looking for. We probably could have done this easier if we did it by hand, because it's, I mean, there's easy numbers. So let's do this. Let's take this U vector as 1 root 2, 0, 1 over root 2, and then compute U1 multiplied with U1 transpose, and that is U1 1 over root 2, 0, 1 over root 2, multiply it with 1 over root 2, 0, 1 over root 2. So usually you take the row and multiply it by the column, right? But then you see that there's only one element in the row, one element in the column. Or you can think about it as this is a 3 by 1 matrix multiplied by a 1 by 3 matrix. And then you're going to end up with a 3 by 3 matrix. So the first one is these two multiplied together. 1 over root 2 times 1 over root 2 is just 1/2. And then the first row, the second column, the first row, the last column. The second row, actually the whole column would make that go away. And then this is 1. Yeah, so we're kind of finding ways to decompose a matrix. We're finding ways to factor a matrix. So here, not only did we factor a matrix, but we're also decomposing it into different parts. So here's one of them. This is U. Actually, that's what we got, right, in Mathematica. 1/2 0 and a row of zeros and 1/2 0 1/2. So we'll do the same thing for U2 and U3. So I think this is what I need. And then we'll do the same thing for U3. So these are the decompositions, or this is the outer products of each of those. We have U2 times U2 transpose is equal to this. And then we have U3 times U3 transpose is going to be equal to this last one here. And so what they're saying here is to complete this thought, this idea, the matrix A is equal to the eigenvalue 7 times this 1/2, 0, 1/2, 0, 0, 0, 1/2, 0, 1/2 matrix plus 7 times this other matrix, U2, U2 transpose, and plus, and then the last eigenvalue times this last matrix over here, U3 dot U3 transpose. Now we were able to take apart that matrix and break it up into these different matrices. Multiplied by their eigenvalues. So we should probably check, since we have it in Mathematica, we should check this if we multiply these things by the appropriate values, right? So if we take our 7 times that matrix from before, and then plus 7 times the next matrix that we got, plus -2 times this last matrix, that it should equal to the original matrix A, right? So after we simplify it and all that. Is it? Right there. So it worked. Whew. That's nice. Okay. So now we're able to decipher this and break this apart. Yeah. What else? Oh, they say something over here. So representation of A is called the spectral decomposition, because A is broken up, breaks up into pieces determined by the spectrum, which is the eigenvalues of A. And then U1 dotted with U1 transpose is a projection matrix, in a sense that if you have a vector x in Rn, if you take x and apply it to that projection matrix, and that's the orthogonal projection of x onto the subspace spanned by u sub j. So ties back into the whole orthogonal business stuff. Is this really heavy? Like hard to grasp? So I'm trying to see if I can come up with a activity for you guys that would require MATLAB and getting an image and finding out the spectral decomposition of an image. That means you guys will have a hard worksheet assignment. Well, I don't know. I mean, maybe a matrix could be represented with a. All right. So, we'll see between now and Wednesday if I come up with a special activity for you. If not, we'll just keep going on. People are always looking for applications, right? You know, what's this applied to? If you really wanted an application to this, we have to dig a little bit deeper with some of the stuff. So, we'll see. All right, let's we can be done. I'm done.